We know from recent lectures that a process is an instance of a running program, and that the operating system is keeping track of various data about all of the processes that are currently running on the system. To do this, the operating system assigns each process a unique identifier known as the process ID, and we can find out the ID of our process in C with the GetPID function. GetPID returns a value of type PIDT, but PIDT is really just an alias for an integer, and so we can print that integer with %d. If we compile and run this program, we get a process ID that just seems like a large random number. And if we were to run the program again, now we get a slightly larger number, and again, and again. Each time we run this program, that creates a new process, and the operating system is assigning process IDs in an increasing sequence. But running a program at the terminal isn't the only way to create a new process. We can actually create new processes in C using the fork system call. Fork is a function that is defined in C on Unix systems, so that includes Linux and Mac, where the fork system call creates a new process, and that new process is an almost exact copy of the existing process. So if we save this code, recompile, and run, now we see that we are printing a process ID twice with two different PIDs. This is because when we call fork, our process gets copied, and the new copy is assigned a new process ID, and both processes continue executing from the next line of the C program. And so each of those processes has a different process ID and will print a different value when they get to line 10. If we had put the getPID call before the call to fork, and now we recompile and rerun, we still get a process ID printed twice, because the fork creates two copies of the process, but since we got the process ID before we forked, the two copies of the process had the same value for the myPID variable, and so they print the same process ID. Let's draw a stack diagram to illustrate better what's going on here. When we run this program, as always, we get a stack with a stack frame for main on the bottom. And our main function here has two local variables, myPID and childPID. And we fill in myPID by making a call to the getPID function. We don't know exactly what happens in this function call, so we're not going to fill in its stack frame, but we know that when it returned, it gave us back a PID ending in 41 that we filled in for myPID. But then we call the fork function, and again we get a new stack frame for fork, and we still don't know exactly what's going on in the fork function. But by reading the documentation for fork, we find that it will create an almost exact duplicate of our process, which means that by the time fork has returned, we will have a new process with its own function stack but that will be an exact copy for our original process. When fork returns, we end up with two almost exact copies of the process. Their state, in terms of the virtual memory view of the process, is almost identical. They have all of the same things in the code segment, in the registers, in the heap, and in the stack. Everything is identical except for one distinction, which is that fork returns a different value in the parent process versus in the child process. In the child process, fork will always return 0, and we're assigning the return value of fork into the child PID variable. And in the parent process, fork will return the process ID of the child. So this is some integer larger than the parent's process ID. I'm just going to guess that it ends in 42, but it might be something larger than that. And so now both processes continue executing from here, and they both called printf, and we passed in my PID as the value for the printf. But in addition to printing out my PID, we could print out the value of child PID. And when we compile and run, we see that one of the processes continued running with a child PID value that was a positive integer, so a valid process ID. And the other process got a return value of 0 from fork. And so when we saved that into the child PID variable, we just had a value of 0. So if we want to use fork to create a new process that will do something different from the parent process, then we need to use the return value of fork to distinguish between which process is the parent and which process is the child. And so, whenever we call fork, we should, in general, follow it immediately by an if statement that depends on the return value from fork. We'll check if the value that we got back from fork was positive, in which case we know that we are in the parent process, and so the parent process will go into the if statement. We know that in the child process, fork will return 0, so here the child process will enter this else if condition. And it's a good idea to also have an else case, because if something went wrong with fork and the operating system wasn't able to create a new process for us, then fork will return a negative number, and so we can detect that error with our else case. And so now we can have our process do different things in the if case and the else case, and thereby have our parent process and our child process do different work. For now, let's just have them print out the fact that they are the parent and the child. If we compile and run, we have different behavior from the two processes, one entering the if condition and the other entering the else, but we're getting the same process ID because we called getPID before the fork. If we move that after, now the parent and the child are printing different process IDs. And in the parent process, we know a little bit more information, not just that fork gave us back a positive number, but in fact, fork gave us back the ID of the child process. And so if we have the parent print the value that it got back from fork, that should match the process ID that the child got from GetPID. So after our call to fork, we have two separate processes that are executing independently on the CPU. And we have no particular guarantees about the sequence in which those processes will do things. To illustrate that, let's add a usleep command after the fork. And if we now run our program several times, some of the time we might get our printouts in a different order. So here we got the printout of the process ID from the parent, and then the parent printing out the child's ID. Whereas here we got the child printing out its own ID before the parent printed out the child's ID. And this is because these two separate processes are both running on the CPU, and we don't know which order their results will happen. Because the computer I'm using has a multi-core processor, it might be that these processes are running simultaneously on different cores, but it could also be the case that they are running on the same core of the processor, and the processor is switching back and forth between them. So if we have different processes running at the same time, in general, we can't predict which order the things are going to happen between the different processes. And so some of the time, the parent process will exit first, and other times the child process will exit first. But a common pattern when creating a new process is that the parent process wants the child process to perform some task, and meanwhile the parent process will wait until the child is done. And we can do that with the wait or waitPID system calls. So we know that only the parent process will execute the if block here, and so we can add a call to the wait function, which will cause the parent process to wait until its child process exits. If we look at the manual entry for the wait system call, wait takes as input a pointer to an integer that it will fill in with some status information when the child process exits. So let's create an int variable. And then we can give the address of our child status variable as the pointer for wait. And so now we might want to print that the child has returned and the status that we got back. And if we compile and run again, now the parent process prints out its ID, and then the child process does all of its work, and then we get the printout from the parent process that the child has returned. So what's happening here is that the parent process is paused on this call to wait until the child process returns. Let's draw a diagram of what's happening with and without this call to wait. To draw a diagram of multiple processes running on the system, we typically illustrate time as going from left to right, and we show the execution of a process as a line in time, where here we have the parent process, and it will call fork at some point, creating a child process that will be running simultaneously. In the parent process, we have our print statement, I'm the parent, and then later we print that we're exiting. And in the child process, we have our print statement, I'm the child, and then later on we print that we're exiting. But what this diagram is illustrating is that we have no particular guarantees about the relative ordering of things that are happening in this process and things that are happening in this process. We know that if the parent process did any work or printed anything out before the fork, then that will definitely appear first. But the next thing that we see might be these print statements from the child process or the print statements from the parent process, and those could be interleaved in any order. But when we include the wait call in the parent, then we have our parent process that forks off a child process. And before the wait, we're printing out I'm the parent. But then we know that the print out that the child has returned and that the parent is exiting won't happen until after the child process has returned. So in the child process, it'll print I'm the child, and then eventually it'll print exiting. And then we can rejoin these lines to indicate that at this point, because the parent process waited for the child, nothing else that happens in the parent process will continue until the child it was waiting for has exited. And so we know that the printout that the child has returned and that the parent is exiting must happen after the child process has finished. And so now we could, in principle, get any interleaving of the I'm the parent printout with the two printouts from the child process, but we know that all of these print statements will happen before we get the child returned print. And so if we run our program many times, we consistently see the prints happening in the same order. Of note, in all of these runs, the child is returning status 0, but if we were to have the main function here return something other than 0, we get a different status in the parent process when wait returns and fills in that status pointer, and this 256 is because the status that's getting filled in is actually an array of bits indicating lots of different information that might be relevant about the status of the child process that exited. And so 256 means that the 256's column, that bit was on in the status integer that was filled in. And if you're interested in what the different bits of that status integer mean, you can look it up in the manual page for wait or wait PID. Let's suppose now that because we're running on a computer with several cores, we want to create several processes to do work for us in parallel. So we might think to call fork in a loop and create several different child processes that will be doing some work for us. Please don't follow along with this example until we get to the end, because lots of complications can arise when calling fork in a loop. So let's say we wanted to create 3 child processes so that we would have 4 copies of our program running to do some work in parallel. So we're now calling fork at the top of our loop, and then the child process will go into the else case, and the parent process will go into the if. If we compile and run, we get a whole lot more output than we maybe expected. And if we count up the number of unique process IDs here, we had process IDs ending in 901 through 909 with 908 skipped. So that means we created 8 different child processes when we meant to create 3. So what the heck is going on here? Let's look through our code and draw a timeline of the processes that we've created. So at the start of our program, we have just our original process, and when we enter the for loop, the first thing we do is call fork. And so now we have separate parent and child processes, and the parent process will go into the if, and it will print, I'm the parent, and then it will wait. Meanwhile, the child process will go into the else, and it will print, I'm the child, and then it will continue executing. So after this print statement, it skips over the else, and now it gets to the end of the for loop and goes back up to the top. And now the child process is calling fork, which means that this process is split, and we now have a parent process and a child process from our child process. And so this call to fork will return 0 in one of those and a new process ID in the other. So for this particular fork, this is the child, and this is the parent of this fork. And so the parent will get the child's process ID, and it will go into the if statement, print, I'm the parent, and wait. Meanwhile, the child process gets an exact copy of the state of its parent, except that the return value from fork was 0. So it will go into the else statement and print, I am the child. And then it will continue executing. It will get to the bottom of the loop, come back up to the top, increment I now has the value 2, and so it will loop again, and this child process will call fork. For that call to fork, the parent is this process, and the child is this one, and so the parent will go into the if statement and print I am the parent, and the child will go into the else and print I am the child. And then the parent process is waiting while the child process continues executing, gets to the bottom of the loop, increments I, and I is no longer less than 3, so it will drop out of the loop and print that it is exiting. When this process exits at the end of main, any process that was waiting for it, namely this parent, will resume executing after the wait. So at this point, we can rejoin these lines. So to figure out what this process is going to do, we need to think about the status of the variable I. So way back at the beginning, we had I equals 0, when we did the first fork. When we did this fork, we had I equals 1. And when we did this fork, we had I equals 2. And each time we did a fork, both processes get a copy of this variable I. And so now, as this process continues, it has I equals 2. So it will print that the child has returned. And then it will go to the bottom of the for loop, increment I, and I is now 3, so it will drop out of the for loop and exit. When it exits, that means that the process that was waiting for it can now resume executing. But this was the one where I had the value 1. So when this process keeps going, it will print out that the child has returned, and then come to the bottom of the loop, increment I, and I is now 2, so we will enter the loop again and call fork again. This process will then be the parent of that fork and go into the if, whereas the new process will be the child and will get child PID of 0 and go into the else. And so here, we are now on the I equals 2 iteration of the loop, which means that the child process will fall out of the loop and exit, at which point the parent process can resume after the wait. And now, since I is 2, when we get back to the top of the loop and increment it, I will be 3, and we'll leave the loop, and we will exit this process. And now, since the original parent process is waiting for this one, it will now get to resume execution after the wait call. But when it was waiting, it had an I of 0, and so when it resumes, it will come back to the for loop and increment I to 1 and call fork again. So here, I is equal to 1, so the parent process will get back the child's PID and go into the if case, printing I'm the parent and calling wait, while the child will get a return value of 0 from fork, go into the else case, and print that it is the child, and then it will continue executing. With I equals 1, when it gets back to the top of the loop, it'll increment I and go again. So this child process will call fork with a value of I equals 2 in both parent and child process. And the parent of this fork will print that it is the parent and then wait, while the child will print that it is the child. Now the child will get to the bottom of the loop, increment I to 3, leave the loop and exit. When the child exits, the parent process can return from wait, and so it will print that child has returned. And then it also has a value of I equals 2, and so it will now leave the loop and exit, which will allow the original process to resume execution, and it will print that the child has returned. But it still has a value of I equals 1, and so when it continues executing from here, it'll go back to the top of the loop, enter the loop again with I equals 2, and call fork one more time. It'll print that it's the parent process, and then it will wait while the child process prints that it's the child. The child process has I equals 2, so it's done looping and will exit. Then the parent process will wake up once the child has exited, and it will print that the child has returned. And then it will be done with its loop when it increments I to 3, and it will exit. And so now we see how we ended up with 8 different process IDs. We had the original process, the first child, the next child, then this one, then we got this child, this one, 7, and then this one was 9, but let's just label it 8 to be clear. This is why we need to be extremely careful about calling fork in a loop, because we could get an exponential explosion of the number of processes with the potential to crash the system. So, what went wrong here? Well, broadly speaking, the issue was that our child processes were continuing to execute this for loop. So the easiest fix in this case would be to break out of the for loop And that will solve the problem here, because the only work we really wanted out of the child was for it to print its ID. But in more general cases where we are expecting the child process to do some work, we need to be careful that we make sure that the child process, when it's done doing that work, doesn't keep on executing code that was intended to be part of the parent process. If we compile and run with the break statement, now we get process IDs 34, 35, 36, 37, so there are only 4 processes like we intended. And if we draw a timeline for this program, here's what it would look like. There are a few more print statements that I haven't indicated, but broadly speaking, we have each child process printing its ID and then exiting, while the parent process is waiting for the child and will only continue after that child has finished. But as indicated by that timeline, there's not actually a lot of parallel work being done, because we only ever have 2 processes executing at a time. If we instead wanted to create all 3 child processes and only wait for them at the end, we could move this wait statement outside. But here is another case where we need to be careful about the distinction between the parent process and the child process. So if we were to run the code as it is now, the child processes would break out of the for loop, and they would then try to wait for one of their children, but since they don't have any, they would be waiting forever. So we need to make sure that the child processes will never execute this for loop. We could do that by either having the child process exit at this point, or by having another if statement that depends on whether we're the parent or the child. Now only a process that has child PID greater than 0, which should only be the parent process, will execute this for loop. And maybe more interesting than looking at the status that we got from the child would be looking at the process ID of the child that has exited. So the call to wait will return the ID of the child that exited. And so we can print out which of the children has exited. And in this case, the children returned in order, 4-7, then 4-8, then 4-9. But there's no particular guarantee that that will happen. For example, we could have the children wait for different lengths of time. So now the child that was created on the first iteration will sleep for 3 seconds, the child on the second iteration for 2 seconds, and the child on the last iteration will sleep for 1 second. And so now we see that the child processes have exited in decreasing order. And so this indicates that the parent process, when it calls wait, it will pause until any of its children have exited. If we instead wanted to wait for a specific child process to finish, we could use the wait PID command. Looking at the manual entry for wait PID, we see that wait PID takes a process ID to wait for, a status pointer, and some options. We can leave the options as 0 for now. So if we want to know which child to wait for, then we need to store all of the child IDs. So let's replace child PID with an array of child PIDs. And so now we'll fill in the return value of fork to the ith entry of this array. And so the first time we call fork, we'll fill in the 0th child ID, then the first, and then the second. And so now we can wait for child PIDs at 0. Let's call this PIDs plural. And I also need to check in the other places the appropriate index in the child PID array. And if we use child PIDs of 0 here, we might have a concern where child process number 2 will have already had some of the child PIDs array filled in when the parent process filled them in on the previous calls to fork. So we had better make sure that we check the last element of this array and that we set all of the elements of this array initially to 0 to ensure that only the parent process goes into this loop. I missed a child PIDs, and I forgot to pass the third argument 0 to wait PID. So now wait PID returned the ID of the first child on the first iteration, and then it returned -1 on subsequent iterations. We can look back at the manual to see what's going on there. It looks like I waited for the 0th process ID every time, and so I got -1 indicating an error because we were waiting for a process that no longer exists. So if we instead wait for the ith child PID, now, even though the children exited in decreasing order, the parent process waited for them in increasing order. So the parent process was not able to continue executing until the child that it was waiting for returned. And so it was waiting on the first iteration of this loop until the first child returned, even though that was the one that slept for the longest. And so by the time this wait PID call returned, the other children had already exited, and so the next two iterations of this for loop were very quick because we were waiting for a child that had already exited, and so the wait PID returned right away. Let's draw another diagram of what's going on here with wait PID. Our parent process calls fork, and the child process will print and then sleep and then exit. But meanwhile, the parent process has gone back to the top of the loop and is calling fork again. After printing that it's the parent on the first iteration of the loop, it will call fork for the second iteration of the loop, and this child will print that it is a child and then sleep and then exit. Meanwhile, the parent process prints that it's the parent, and then calls fork again on the third iteration of the loop. It again prints that it's the parent, and then the parent process will call wait PID. The thing that the parent process is waiting for at this point is specified by the PID that we gave to wait PID, and since we gave the PID that we got back from the first call to fork, this one will wait until the first of these child processes has completed. Then we'll print that the child has returned, And then we'll wait again, and this time we're waiting for the second child process. When it exits, we'll continue to the next iteration of the loop and wait for the third one. And so we have that the parent process will only continue when the first child exits. And since we don't know about the relative timing of processes on different lines, it doesn't really matter that this first child exited first. The only thing that we can reason about in the comparison of these processes that will definitely be consistent is that the parent process will wait for the first child process first, and it will only continue when that first child has exited, and then it will continue again when the second child has exited. And so even if the second child process actually exited before the first one, we will never get to this point until both of the first two children have exited. So all of this is well and good, but it seems pretty awkward that we are splitting our programs in two and always getting a duplicate copy of exactly the same program we were already running. Oftentimes, when we create a new process, the reason we want to do that is because we want to run some other program. And the way to do that is with the system call exec. Let's go back to the version of this code without the for loop. That looks good. And let's think about having the child process execute a different program. We do that with another system call function. These functions that I'm calling system calls are asking the operating system to perform a task for us. And so exec VP asks the system to replace our process with the starting point for a new program. execvp expects two arguments, which are the program we want to run and the argv array that will be given to that program. So let's build an argv array for a program we might want to run on the terminal. I'll make this a local variable, but it could just as well be a dynamically allocated array on the heap. And in the argv array, we want the first string to be the name of the program. And then subsequent strings are arguments to that program. And then, as we've seen before, the last thing in the argv array is a null pointer indicating the end of the arguments. And so now I can pass into execvp the name of the program that we want to run, which in this case is the 0th element of our args array, and also the command line arguments, which are just this whole args array. And if we save and compile and run this program, now we get the parent printing out its ID and the child's ID, and that the child returned and the parent exiting, but we don't get any of the print statements from the child process. We never saw the print statement for I'm the child, and we don't see that the process with the child's PID exiting. The reason is that this exec system call has replaced the state of the currently running process with the start state of a new program. Specifically, the program we ran was ls-l, and so that had the effect of printing the output of an ls-l command. And because we replaced the entire state of the current process with the start state of the ls program, the remaining code after the execvp was not executed. If we take a look at the manual entry for the exec function, we see that exec and all of its variants only return if there was an error. Because we are replacing the current process, we will never get to the following line unless there was an error. And so really, after the call to exec VP, we should have an error message because if we tried to exec and it didn't work, now we have a process that we forked that we were planning to use to run the ls program, and that process is now continuing to execute past the point where we expected it to have been completely wiped out and replaced with a different program. So after a call to exec, we should always have an error message and an exit, because if exec ever returns, that means something went wrong. An example of something that could go wrong is if we tried to call exec, but gave it an invalid program name. I need to include and so now we see that since we had a typo in our ls, the exec failed. We were not able to start a program called LT, and so we did continue past the exec call, and that's why we want to print an error message and exit. So with fork, we have the ability to create new processes. With exec, we have the ability to start those processes running some new program. And with wait, we have the ability for the parent process to synchronize with the completion of the child process. And it turns out that exactly these system calls are being used to run the command line terminal that we've been using all semester. When I run ls in the terminal, the shell, which is the process that is running in the terminal, will fork a new process and exec the ls program and wait until ls is done to give me back my command prompt. And this is precisely what you will be implementing on the last homework of the semester when we create the cat shell.